Now we shall learn about rectangular components of a vector. Finding components of a vector is an important tool in simplifying a vector and being able to study it in a more simple way, and it has got a lot of applications in physics, class 11 physics especially. So, let us understand what components of a vector means and then what are rectangular components. Okay. So, to understand this, let us work with a vector. Let us call it vector A. And let us say vector A is such that it makes a certain angle which we can call as theta with the x axis, the horizontal axis. Then naturally it will make an angle of 90 minus theta with the y axis, right? We understand that this angle will be 90 minus theta, then the angle that vector A makes with the y axis. Now, finding out the components of a vector about any other direction, it's a simple process. What we do there is, for example, here in this figure, if we try to find out the component of vector A along the x axis, what we need to do in order to do this is, from the tip of the vector, as the tail of the vector A is coinciding with the origin, the point x is equal to 0, from the tip of the vector we drop a perpendicular which falls and intersects the x axis at a certain point. If we are able to measure this distance OP, the distance between the origin, the point x is equal to 0, and the point P where the perpendicular dropped from the tip of the vector A hits the x axis, this length is called the component of vector A along the x axis. We can write it like this, A with the subscript x. Similarly, if we drop a perpendicular from the tip of the vector onto the y axis, then this length, we can call this a point Q, the length OQ will then be called the component of vector A along the y axis, AY. So, for that matter, the component of a vector along any other direction with which it makes a certain angle and we know that angle, all we need to do in order to find out the component of the vector along that direction is we drop a perpendicular from the tip of the vector to see where it cuts that axis, and then we just measure this particular length. This becomes the component of the vector in the particular direction with which it makes a certain angle. Okay. So, for now, these two components that we have obtained here, the component of vector A along the x axis and the component of vector A along the y axis, these are special type of components, we will see why. But see that these two components themselves are perpendicular to each other, aren't they? If I talk about the vector Ax, which will be a vector which will point from the point O to the point P, this can be called the vector Ax, the component vector. And also the vector Ay, the component vector which points from point O to the point Q. These two are called the component vectors of the vector A, and these are perpendicular to each other. Since these components are perpendicular to each other, they are called rectangular components. These two components together, they tend to form a rectangle. We shall see how when we proceed with this. So, for now what we will try to do is, we will try to find out the magnitude of Ax and Ay using trigonometry. You can see that in the triangle OP, and let us call this point as R, OPR, which is a right angle triangle of course, we can easily write the base OP by the hypotenuse OR as cos of the angle theta. Now, the length OP is nothing but Ax. So, from here we can write Ax by the length OR is nothing but the magnitude of vector A, which we can write as A. So, Ax by A is what we are getting as cos theta here, and we can get the value of Ax from here as A cos theta. So, this becomes the value of the component of vector A along the x axis. Ax is equal to A cos theta. Here A is the magnitude of the vector A and theta is the angle that the vector A makes with the x axis, right. Similarly, if we try to find out the y component, see that this particular length here, this is the same as the component Ay. which for the triangle OPR is nothing but the opposite to the angle theta. So, we can also write the length PR, which is the opposite, by the hypotenuse, which is OR, will be sin theta by definition, which implies PR is nothing but AY by OR, which is nothing but A, is equal to sin theta, and from here we get the value of AY as A sin theta. So, this becomes the y component of the vector A. Now, what we have obtained here are just magnitudes. In order to get the vector components, that means vector AX, we need to add the direction of the component along with its magnitude. So, vector AX will be the magnitude AX times its direction. Now, as we see here, this vector AX is pointing along the positive x axis. So, we know what is a unit vector that points along the x axis, right? It is I cap. So, if I just write I cap over here along with AX, I will get the magnitude of vector AX and its direction together, right? So, from the value of AX that we already know, we can also write this as A cos theta into I cap. On the same lines, vector AY, the component vector along the y axis, can also be written as AY into a unit vector along the y axis, which we know is j cap. So, this will be equal to A sin theta into j cap. So, these two component vectors that we have obtained are called rectangular components of vector A. Okay. Now, what is the importance of finding rectangular components of a vector? Let us look at that now. Look at the two vector components, vector AX and vector AY in this figure, and see how they are placed. Vector AX is pointing along the x axis, vector AY is pointing along the y axis. Both of them are connected together at the point O, the origin, and it is from that origin that we also have the vector A, which is forming the diagonal of the rectangle formed by the vectors AX and AY. Does it make you recall something? Does it look like, does this figure look like the figure that we have studied for vector addition using the parallelogram law? If we consider the vectors AX and AY as the two sides of a parallelogram, then we know that their diagonal, which in this case is nothing but vector A, will give their resultant, right? So, from this figure we understand that the vector A can be written as the sum of vectors AX and AY. And this is where the importance of rectangular components lie. We say that the sum of the components of a vector gives us the vector itself. Here, when we add vectors AX and AY, we get the vector A back. So, what we have been able to do by finding rectangular components is, we have been able to split our vector A into two mutually perpendicular vectors, such that when we add those two vectors back, we get the vector A, right? So, this is where their importance lies, and we will see there are a lot of applications associated with this. Now, moving further, we can also write this as AX I cap plus AY j cap, right? Vector AX and AY can also be written like this, which if we want, we can also write as A cos theta I cap plus A sin theta j cap, right? So, we say that in general a vector A can always be written in terms of its rectangular components. Fine. Also, if you look at the figure carefully, we can find out the length of the vector A, that is the magnitude of vector A, that is the length OR, in terms of the magnitudes of its two components. As you can see here, we can use the Pythagoras theorem directly to say that the magnitude of vector A will be nothing but square root of AX squared plus AY squared. How do we get this? We know that the vectors AX and AY are perpendicular to each other. So, when we try to use the formula for resultant of two vectors as A squared plus B squared plus 2AB cos theta, the angle between the two vectors here is 90 degrees. Vectors AX and AY are perpendicular to each other. and we know that cos 90 is 0. So, this third term will go away and we will be left with only this much. So, this is the expression that we have got. This gives us the magnitude of vector A in terms of its components, which is another important expression to remember. Also, we can find out the value of angle theta in terms of the components of the vector. That is also an important expression that we can get here. See that we can also write tan theta is equal to the opposite by the base, which in this case will be ay by ax, right. So, a sin theta over a cos theta, which you see is coming out to be tan theta itself, isn't it? So, this is how we can connect various things associated with a vector in expressions. All things are connected. So, if you are able to connect things well, if you know the basics well, you can always use these basics to solve questions of different sorts, right. We can take up a question here to understand this better. Let us say there is a force vector F having a magnitude of 20 newtons and it is directed such that it makes an angle of 30 degrees with the x axis. So, our force vector looks somewhat like this. This is the vector F and it makes an angle of 30 degrees with the x axis, horizontal axis. The question is to find out the components of this vector F along the x and the y axis. Fx and Fy is what we are supposed to find out. So, look at this. We can easily say that by dropping the perpendicular onto the x axis, this length, which will come out to be nothing but f cos theta, will be the horizontal component Fx, whereas the vertical component can be obtained by writing f sin theta using, we are using trigonometry here, right, basic trigonometry. So, that will be nothing but the y component Fy. So, here Fx will be f cos theta, which will be 20 cos 30 degrees. We can substitute the values. Cos 30 is root 3 by 2. So, this will give us 10 root 3 newtons as the answer. Whereas, Fy, the y component, which is f sin theta in magnitude, will be 20 sin 30, which is sin 30 is 1 by 2. So, this will be 10 newtons.